Yep, recording is started.
Okay, thank you. So yeah, so we have today's session of topological sort, and uh, this is a handout for the topological sorting. And so topological sorting, we have like a lot of questions come up, like you want to order, basically, if you have given some uh, packages or like sometimes courses which needs to be done before, like how you will be ordered, so that you need to install, for example, let's say example of the packages, you need to install that package before, so which is a prerequisite of the package, so that other package you'll easily install that. So this is one thing which can be resolved using topological sort. And okay, someone is saying we have an audio issues. Sorry. Can you see the screen, correct?
Yes.
Yeah. Okay. So yeah, so these are kind of a questions which are related to topological sort. So this is more like how we order on the basis of dependencies. Like if some course is dependent on before other course, how we order them. And there is a difference which this particular topological sort is different from DFS. Like what we do for in the DFS, like the proper DFS solution, we just visit each and every, for example, vertex till we and put it in a stack. So, and we print each one by one when we are visiting. But here, until unless you complete all the children's of the all the vertices or all the children's, then you put that in your stack. So let me share my screen for my definition. I think it's small screen. 1 second. Okay, so this is the definition, like what's the main difference between DFS and topological sort. That we in DFS we start from every vertex and we print it, like, and then recursively call all its adjacent vertices. And but in topological sort, we first print. We don't print the vertex immediately. We push all its. We go to all adjacent vertices, then push that into a stack, and then finally print that stack. So we have two approaches for this. One is DFS and other is BFS. So let's take example of this one. We have.
Hi, is anyone talking? We can't hear anything.
Sorry?
Somebody is saying they cannot hear, but I believe most of us are hearing it. So
yeah, I can hear it too.
yeah,
Yeah, I can hear too.
Maybe it's an audio problem. They need to log out and log in again.
Yeah.
Okay.
Yeah, keep going. Like I will like reply to that individually.
Okay, thank you. So, okay, so this is one example. Let's try to solve. Let me explain first how we are solving it, like in DFS, and then I'll go to BFS, and then we'll start solving a problem. So the main thing is, if you know the algorithm, you can apply this to any problem which we'll be solving today with a little twist. So here is, we have a graph which is a DSE. The first main thing is this question is always be able to solve only when there is no cycle. And if there is a cycle, then this is not a topological sort for the graph. So
Sonia, one
yeah.
quick thing. I'm trying to understand, like, when you say comparing DFS with topological sort, right? DFS is like, uh, it's a way to find the path or like to search. That's how it is, right? Topological sort is more of a sort, right? So how is
Yes.
sort and a search being compared here?
So so the thing is, like, in DFS will be like, it's also both are how we solve the graph problem of DAG, like acyclic graph. We can solve that with the DFS and with the topological sort. So that this question is these questions are particularly related to the graph with the DAG. So in DAG, we'll be like how we recursively call and print. For example, if you want to print all the nodes of the graph like this, we have a graph and we want to print all the nodes. So we'll be printing in DFS like, so what should be the answer in DFS? Can you give me, like, we visit 0,
Take 0, you go to
1,
going depth first, right? You go to 1,
yes,
and then probably you'll have two nodes for it, but you pick 1 and go depth. Go to 2.
yes, yes,
You have 3, 4, 5. So let's say we pick 5.
okay,
Sorry, 2, 3, 4, 5. Right? I could either pick 3. I would say 3. Let's pick 3,
mm-hmm.
and then from 3 I would say I have 4 and 5. Then I go to 4.
Mm-hmm.
Then I go to 4, I have 5, and then now there is nothing to visit, so I come back to 4 and see if there is anything else to visit. No. Then I go to 3, then I saw that 4 is already visited. 4 is already visited, and then I see if I can go to 5, but 5 is already visited. Then I go back to 2. 3 is already visited. 4 is already visited. Sorry, 3 was initially visited. I go to check 4. It is visited. 5 is visited. So go back to 1, and similarly go back to 0.
Mm-hmm.
So that could be done. Yeah.
Okay.
So this
Yeah.
way, I made sure like I've visited all of them by following the depth first way.
Yeah. So this is this is the thing. Like, I think this is not so good example of comparing the DFS with the BFS with the topological sort. Let me see one more example of it.
No, but I think the idea is that if you think DFS is like any other traversal, like pre-order, post-order, and something, we're just printing as soon as we visit a node.
Yes.
And then we're going. And there could be multiple paths. There could be multiple ways to print. 0, 1, 4, 5, 3 could be also one answer.
0, 1, when you go depth first, right? You are saying,
Yeah,
like
0, 1, 2, 4, 5.
Yeah, it could be like 0, 1, 2, 4. 4, 5, 3, or 2,
Or
5, 3.
0, 1, 3, 4, 5, 2.
Yeah.
So there could be multiple ways. I think what Sonia is trying to say that it's just, if we just print out as we are doing, that will just give how we are traversing from wherever we start. If we start from any other node like 2, then we have to do 2,
Yes.
4, 5, and then 0, 1, 2, 3 will come later.
Yeah. So here is like we are picking. We can pick any vertex in the topological thing initially.
Not in the topological, like doing DFS also, we can pick from any node.
So I was trying to see one more example. This is very big. Okay, so you can see this picture. So what would be the DFS of this?
So you were trying to see if you have visited all of them, right? So I could start from anything. So let's say I start from 0, and I say like, okay, 0 is visited and there is no other nodes. So then I start again from 1, and then 1 also is the same. So I go to 2. 1 is done and I don't have any other way. So then I go to 2. So from 2, I have 3, so I say 2 and 3 are visited, and 3 I try to go to 1, but 1 is already visited, so, and 3 doesn't have any other way. So yeah, 4 and then 5 similarly.
So the output should be like something.
The way I picked is like taking all the vertices in a loop, right? So 0, 1. Oh, okay. I'll say 0, 1, 2, 3, 4, and 5 actually. Yeah.
And that is regular DFS, picking up any
This
node
is an
and going into
example
that.
of, yeah,
Regular
regular DFS. But in topological sort, we only go when like where it is, we recursively call all the vertices, like all the children's. We first complete all the children path, then we put the node itself in a stack. For example, here we have, let's say we are starting with 5 in topological sort.
Mhm.
Well, let's say we are starting with 5 or 4, any vertex you can start. And you first see you'll be going 5, let's say you'll be going 2, then 3, then 1. So I'll put in my stack 1. And then stack is like, yeah, I'll put that push 1, then it goes to 3, then it goes to 2, and then let's say 0, because we can't visit 5 because its children's 0 is left yet. So we print, we push 0, and because 0 is not, there is no other than 0, and so now we can push 5. So you can see there is another vertex which is left, so which is 4. So so this is the thing, we need to traverse all the nodes. So the answer here, it is like, if we pop our elements, the answer is 4, 5, 0, 2, 3, and 1, or 5, 4, 0, 2, 3, and 1.
Okay.
So yeah.
Seems like this is a solution, but why we are doing this?
So the main logic behind this is like, we need to finish all its like dependents before pushing its the main initially one, like the start point. So the main thing is for example, let's say this is one course and these are the 2 courses which are prerequisite, and if you can only do these courses 2, 0, and 1 if you have done these courses before. That's the way which I am saying. Like,
so basically we have to finish the prerequisites. So basically we have to visit the prerequisite first and then have to do. And to find the order, this is one way of doing.
Yes, this is the order. This is the way how we can order it.
Yeah, so the topological sort will, give all the nodes like in one direction, going forward in one direction, which is useful while solving these problems.
Yes, so that's correct. So if any of the question with you want to give print like the order of it, then topological sort is one way. And by the time, if you want to know the cycle along with the question, that's you can find out in the algorithm.
Basically, if there is a cycle, then there could not be a order.
Yes, there cannot be an order, and so there is no solution in that.
So think in that way, 5 is dependent on 0. So this is like a deadlock.
Yeah,
0 needs 5, 5 needs 0. So there could not be answer.
Okay, so is there any question about how the DFS approach work? The DFS approach of topological sort work. So the main logic is this is an algorithm, do DFS for any vertex after visiting all of its children, then out the element in a stack, then output your element in the stack, and then pop elements from stack and print them.
So basically we can even put them in a list. Only thing is like at the end you have to reverse it.
So
Yeah.
can you walk through one more time the 1320 what we are trying to put in the stack? Like we start with a random node, right? The node what we are starting one as a random node, and one doesn't have any children, right?
Yes.
I mean, one doesn't have any dependencies. So now,
let's say if we are starting from any vertex, if we are starting from 0 as well, you are seeing.
okay, so 0 doesn't have any dependency. So 0 is the first
So
element in
if
the stack.
we can put that in our stack.
Okay.
So as soon as all its children are done, that guy will go in a result set. Here the result set is stack.
Yes. So
okay, so 0 goes in, and then we can pick any node, or
yeah, we can pick any node
which is not visited.
Suppose I pick 5. So now I will go and see all its dependencies or subnodes.
Yeah, we'll go to 2.
Okay.
We'll go to 2, and 2's children is 3, and 3's children is 1.
Okay.
So there is no children of 1, we push 1. And then we'll come back to 3. And then we'll come back to 3, and then we'll come back to 2. And then there is another node, 4.
So do we have to maintain 2 stacks here? Like one is for the parent, and then for the children's, it will be a recursive call. Okay, got it.
So there will be one more visited set, like any other regular DFS.
Okay.
So yes, there would be a set to see if we are traversing that path. Is there any node which is already present in that path, which you have already?
No, that is a different thing. But to see if we have already done with that node, that is a visited set. But to find cycle, there is a different approach.
Yes.
Okay.
Okay. So is that any doubts in this? We'll solve the problem, then it will make more clear, I think.
But I think you can talk about a cycle, how to find a cycle. So if there is from 0 to 5, what?
So if there is let's say if we have 0, there is a 5, 0 is dependent on 5. Here, when you are saying the arrow is coming, it's in degree of 0. 0 is dependent on 5. And say we have one more, one second, like this, and 5 is also dependent on 0. Then so now there is a cycle. Then how we'll be able to find that are we able to solve this problem or not if there is a cycle? So that thing is we can take one current stack, which is like while we are traversing that path, and if that node is already present in that stack, then which means that there is a cycle. For example, if we start from 5, then we go to 2, then we'll go to 3, and then we'll go to 1. So this way we printed out 1, 3, 2, I think, 1, 3, 2, and 5. So and we'll start with 0 again.
So let's say you start with 5.
Yeah, 5, then 2, then 3, then 1.
Yeah,
and
then you come again to 0.
Here is like 1, 3, sorry, 2, and now we can't print 5 because 0 is dependent on 5. So we'll go to 0, but 0 is uh, 0 is there is a 5 is also dependent on 0. So because 5 is already visited, so we have one visited set, which is where we can push 5, 1, 2, 3, and if we are now visiting the 0, we can push 0. So if now 0's children is 5, and 0 5 is already in visited set, so we can't put that 5 again.
No, I
And
think the thing is, like, if in your current call, if you see something again, so there is two concepts, visited and visiting.
yeah, so this is a visit, like we are visiting over here, and there is another set, which is, let's say we have a current path which we are following, let's say.
So your current path is 5,
Yeah.
0, and you again see 5,
Yes.
which is in your current path. So that means there is a cycle now.
Yes. So this means that we have a cycle and we'll be immediately return false or something. We'll not be able to solve this. Is there any doubt in this?
So what will be this current path be? Will it be something like a vector, or it will be a stack?
You can take it as a list, or
it should be like a set, so you can easily find out.
It should be a set. Yeah, okay. It should be as a set, because.
But can't we use the visitor itself in this case then?
So visited is something which you have already done. But so in this case, you are done with 1, 3, 2. But visiting is something which is in the current stack call. So 5 went to 2, to 3, to 1. So 1 is done, 3 is done, 2 is done, but 5 is still active. And then it goes to 0. And from 0, it again comes to something which is already active. Think in that way, which is already in the stack call, active. Other things 2, 3, 1 are already done.
Okay. Okay. Thank
you. Yeah.
So can it use to find a cycle in the undirected graph?
So
how there could be a cycle in an undirected graph?
Oh, I mean, yeah. So there's no direct. Can we find a cycle there?
No, but directed graph does not. Undirected does not have even a concept of a cycle.
Cycle, yeah.
Why not?
Pointed edges.
I think if it's undirected, then that means there is a cycle. There is a cycle everywhere, right? I mean, if there is no direction, that means everything is connected to everything.
Yeah, so there can be two flow thing going on. Yeah. So in undirected, there can be no any arrow like this. If you are saying this 5 and 0, this is automatically saying 0 is dependent on 5 and 5 is dependent on 0.
Yeah, I don't mean that. What I mean, like, if the cycle is between, if we have 0 connected 3.
So you're saying that 0 is connected to 3?
Yeah, and then
in undirected or directed, you're saying?
Undirected.
So, but this is a concept for, I think, directed only. We can't go to undirected in topological sort.
Yeah, I think
in the
topological sort has that constraint. It has to be directed and acyclic.
Yes, it's a definition. Topological sort of is that only that for only directed acyclic graph.
Yeah, I think that when we define a cycle, we say that the path has to exist like that. If you look at the first one, right, we say cycle because there is a direction from O to 3 based on the direction. So yes. If there is like no direction there, so there is nothing like you can go from 0 to 3. I mean, you can go any direction. So that way there's no path. The cycle is mostly based on the path.
So
So it's
cycle,
not,
yeah, sorry.
yeah.
So
Yeah,
cycle we are trying to say is like in this DSG, in topological sort, let's take an example. If this is one course and this is another course, and this course is dependent on this course, and so you need to complete this course before doing this course. But if this is also, we need to complete this course also to come before this course, then this means that is a cycle. We can't do these two things at the same time because one is dependent on other. That means we have a problem and we need to change something. That's a one example, real-time example of this usage. Is that clear? Your point?
Also, yeah, exactly. I mean, I just want to add here, like generally the way I understood the topological sort is, as Sonia was saying about the real world example, right?
Mm-hmm.
So whoever is in the industry, we have a build system, right? In general,
yeah.
When we build our code, that depends on something, and that code depend on 4 other modules, and they depend on some other sub modules, right? So unless that sub module get built, you cannot build your like the top level code.
Exactly. Yes.
So that is the way I understand this. So if your code is dependent on multiple things and there are sub modules which needs to be built first, and then you have to come one level up and then keep doing it in a recursive way, right?
Mm-hmm.
So unless the whatever is at the leaf node that get built, you cannot build the code which is at the level above it, right? And as soon so there is a direction that you go from the top to certain level till the leaf, and if it become a cyclic, you might see that you get an error that you're trying to call a code which is creating a cycle in your code, and you get an exception, cyclic dependency exception.
Yeah.
Yeah. So that is the way I have understood topological sort, that you have to build the lower level, the leaf level modules, sub modules, and then go one level up, and then again keep going at the top level. And if there is a cycle, that means the code will fail and there will be a exception in the build.
Mm-hmm.
Another example is cloud formation stack. So think you have a Lambda which is dependent on SQS. So first SQS should be there, then only the Lambda can be created.
Yeah. Yep.
Mm-hmm. Yeah. So yeah, there are many more examples of these nested things. And so things like if we have a cycle in there, we'll not be able to solve. So first thing is we need to resolve the cycle if we want to build something. Okay, so this is for the DFS approach. So there's one more approach to solve this topological sort is other is DFS. Okay. So in BFS, how we are solving is like think we'll be taking some kind of a degree. For example, how many in degree is like how many nodes are coming to one, like in degree, like one is dependent on how many nodes, which is one. And so I'll write down here the basically, so I'll write down how many in degree of states. For example, 0 has in degree 0. 1 has in degree 1. And 2 has in degree 1. So I think, are you able to understand what's the in degree over here?
So 1 has in degree 0 also, right? I think 1 has in degree of 0 also, right?
So that's why its count is 1. So I am just typing how many count is there.
So that is a count. Okay.
So
Yeah,
that's like the number of dependents on that particular node, right?
Yeah, correct. So and three is dependent on like 3 nodes. 4. Let me 4 is 2. and 5 is 3. That's correct?
Yep.
Okay. So we need, first of all, to find the in degree of these. And so what's this algorithm is saying, like we need to compute in degree of each vertex and initialize the count of visited nodes as 0. First of all, we need to make the main thing is we should be sure that we have created all the in degrees of every vertex. Will not be like will not put only the in degree which has some value. We'll need, like, if there is no in degree of that vertex, still we need to put that in our, let's say, in a map, so that we know which are the in degrees of every vertex. So here is 0. So the other next step is we need to pick all the vertices with in degree 0 here and put it in a queue. Let's say we have a queue and I put 0 in my queue, because its in degree is 0. Is that you able to understand this step, why we have put 0 in there?
Yeah, that's clear. Yeah.
Yeah. So next is we remove a vertex from queue and then increment the count of visited nodes by 1. So that's a different, this step can be or cannot be needed to check the cycle. Like this is like you can create a count, like whether you have visited all the nodes or not, and at the end you can check that your count is equal to the number of nodes, which are number of vertices. If it is true, then you are like, okay, then we have an answer. Otherwise there is a cycle. That step can be like if that question is already saying you cannot accept like there is no cycle in it, then you can skip this step. Next is like here, we'll start with the queue. For example, if we will remove 0 from our queue and we'll start and this is a result set, and we'll put that queue 0 in our result list. So now next is we should visit all the nodes of 0. We'll be having another graph where is like we'll be like which node is it, whose are the children of that node. For example, now we know that 0 has children 1 and 3. So we'll decrement over here 0 and here 1, and in queue we only put that node which has its value 0. So now we'll put 1 over here and we can delete or not from here. It's your wish. The only way, the main thing is we can main step is if in degree node is reduced to 0, add it to the queue. Is that step clear? Why we are putting 1 over here? Because
it's like BFS, sorry, you visit all its neighboring nodes, but only put them where the in degree becomes 0. Basically, if I remove 0 from the picture, then 1 should be a starting point. So basically, if pre-request 0 is done, then 1 should become a starting point, and that is true. Because
yes.
So think like somebody did a course 0 and it is gone, and now only 1 is there. It does not have any prerequisite, so we can put 1 in the queue.
Yes. So now we'll need to visit all its one's neighbors, one's children's. So first of all, we need to remove 1 from queue and put it in a result set. And we know that our children is 2 and 3. We'll remove 0, we'll decrement the count of in degree. Here we'll need to.
So 0's in degree was 3 initially.
Yeah, so I think I have already removed it. So let it be like 1 only. So now we'll put 2 over here. because three still has, is it like I need to put 0 over here? I forgot. Because I am visiting 2. So yeah, 2's children is,
I think you decrement it once after popping from the queue, right? Or
okay.
removing it from the queue. Yeah.
I am lost.
Who will go to the result set?
So 2 is going to the result set.
Yes. Yeah. Now you can decrement it. You decrement the 3.
Yes.
Yeah.
So now we'll put 3 over here. And 3's children, sorry, this should also reduce to 1 because 4 is dependent on this. 4 and 5 are dependent on over here. Sorry. Is that step, or I should repeat that? Because 3 has 2's children are 3, 4, and 5. We need to decrement them. When we are decrementing it, 3 becomes 0, 4 becomes 1, 5 becomes 2. 5 has 2.
Yes. Yeah.
Yeah. So now we put 3 over here. Why? Because its in degree count is 0. So we will now remove 3. We put in our result set, and we'll start visiting the nodes of 3. Now 4 will goes to 0, and this will goes to 1. So we'll put in our queue 4. Still we have some node left. So now still our queue is not empty. So we'll remove this node. We'll put it in our result set, and now we'll visit the neighbors of 4, which is 5. Now we'll remove 5 in in degree, and now we'll put that in a queue. And so next step is to remove that. We'll remove that, and there is no element left. So this is our answer. 0, 1, 2, 3, 4, 5.
So first you have to traverse the whole like this graph to find the degree, and then this queue will have all the dependency of a node at first, and then we keep on dequeuing the queue, or there'll be some different data structure which will maintain that.
So queue is one data structure which we are using to find the this result set. So initially what we have to do, we need to make what are the children's of that particular node and what are the in degree of it.
So the only condition to add to the queue is we add only the nodes which at that point of time whose nodes in degree is 0. I think
Okay.
the only difference, right, compared to BFS?
Yes.
Okay.
I think this can be easily understand when we'll first try to solve that course schedule our first problem with the BFS. So the main logic is this, but we can start our problem.
So you need two, okay, you need a queue and two map, right? One for in degree and one for, like you say, what are the children of the of this node? Is that right?
I'm not able to follow.
Yeah, so basically we need three things. One, we need a graph to represent kind of an adjacency list. And one, we need a map to tell what is the in degree of that nodes. And third one is the queue.
And in that in degree, can we be able to find a cycle?
Yes. So basically, there are two ways to do that. Sonia, can you share your one? No?
Yeah, I can share. I think.
So the easiest way is.
So the main thing is if you can maintain that count. Like I've written that step over here. So that the reason why I have increment the count. So for example, when we are dequeuing our removing our nodes, we can increment that counts of the nodes. And if those counts are not equal to the number of course vertices or nodes which we are already having, then which means that there is a cycle. The reason behind is like, for example, let's make a cycle of 5 to 4 as well. So while dequeuing, sorry. So so last step was 5. So 4, last step was we were having inbounds in degree of 4 with 2. Now, if we draw that line like this over here, the in degree of 4 would be 3. Correct?
Yeah.
And so while we are removing it, let's say we are removing it, and 4 and 5's in degrees is that the same 3, and so we'll not be able to print that. Let me make that over here.
So basically, it will never go to your result set. So if your
Yes.
result set size is less than the number of nodes, that means there was some cycle.
Yeah. So sorry.
I'm trying to say that at the very end, when we put 0 to 3 in the result, and the integrate of the 4 and 5 will be, both of them will be 1, and there's nothing we can add to the queue, and then we'll stop there.
Yeah, so yeah, that's correct answer. These both will be 1. There is no, and the queue is empty because we'll not be able to add anything. And so basically these 2 nodes will not be there. So this is unequal count. And so there will be a cycle.
I think you will be able to add 1 node, at least 4.
That's not possible.
Yeah, there's only, yeah.
Sorry?
I think 1 node you will be able to process 4 or 5. But
4 will never be added to the queue because the integer of that 4 is 1 at the time.
Yes, there will be some logic, like it won't be automatically, it won't able to go in the queue. If it can't go in the queue, it won't come to the result set. So result set size will mismatch the number of nodes, and that is one way to find if there is a cycle.
Exactly.
Mm-hmm.
And I wonder what's the running time of this algorithm. Seems that the running time will be much higher than the DFS solution, I guess.
I think it should be less.
It should be same. You're visiting each node.
This is V plus E, which is like order of vertices plus edges. And we are traversing each node.
Yeah, because in the DFS solution, we can visit each node exactly once. And in this case, we need to visit the node multiple times. So that will be much higher than the DFS solution, I guess.
How we are visiting multiple times?
Both the case same, right? Like here in the BFS, we visit only when the in degree is 0. And,
but we will decrease the in degree. So let's say we are visiting 0 once, and we will visit all its children to decrease their in degree. So the node 1 will be visited once, and the node 3 will be visited twice here. Oh, sorry.
We access the node to reduce the in degree, but we do not traverse that path.
But that will be accessed.
Yeah, it's just an O of 1 operation, right? It's just a map.
Yeah, when we each node, then we can at most visit the big O of n nodes because they are their children. So finally, the overall running time in this case could be big O of n squared.
Why n squared? I'm not able to.
No,
so
because here you're reducing the in degree, but in the DFS, you also again check whether you maintain a visited, and you again check against a visited node, whether you're already traversing that path. So when compared to both, Here your in degree is taking care of visited, but in DFS you're maintaining visited set or
yeah, something like that.
So what do you think the running time of DFS solution?
The runtime should be same, but the only thing is in DFS you need to maintain one more extra data structure for visiting, like I don't know if you, because I think we can't do it in one data set, visited and visiting.
Because in this case, in the BFS, at least I can see we are maintaining the in-degree number for each node. So this at least one actual running data space for each node, and we also maintain the queue.
So that's a memory we are taking, like creating a map. So to make our
you're using the make, okay, using the map.
Yeah.
Seems like both have similar data structure.
Yeah, both have same complexity, I would say.
I don't think so. So what do you think that's BFS running time?
See, actually, we will insert in the queue only if the in degree is 0. So in this case, 4 and 5 will always have some in degree value. So it's not going to be inserted, and therefore your queue will be empty before that. So you can exit that BFS.
Yes, but I think, but we're discussing about the memory map between DFS and BFS. So memory footprint for BFS is there would be visiting, visited, and it is using recursion, so it would be using a stack internally.
Yes.
Yeah. Here it is using this in degree map and the queue.
No, they use an extra map, right? The map, they track the parent of the current node.
Oh, so that will be there in the DFS also. The adjacency list we need in both places.
Yeah, that's needed in both places, and we have that kind of
No, the other one, the stack already. The stack is the node on the current stack is the one that track it.
No, but
right?
stack. So how you will know? So if you have to do DFS of this graph also, you should be knowing zeros children are 1 and 3.
No, I'm talking about DFS. In the DFS,
also,
yeah, the stack is the one that maintain the parent.
No, but how you will know zeros children are 1 and 3? You need some kind of a adjacency list to say, okay, from 0 I have to go either 1 or 3.
You mean in the DFS?
Yes, in DFS.
No, the stack, let's see, we put the, node 0 on the stack, right? And node 1 on the stack.
How
node 3 on the stack.
You have to
so this is an example of DFS. Like, let's say we have a 5. How will we be able to know what are the children's of 5? There can be 3, 0. There is some kind of a list or something which tells us that these are the only children of 5. So similarly in DFS also.
No, but if we visit 5 right there, right? And you put 5 on the stack, right? And you go to 0, right? And now 0, you go back to 5. And you know that, stack have a 5. That means 5 have to be the parent of 0.
So
before that is a visiting set. So can you write all the data structures we are using here? One is the adjacency list.
Do you have a code for this? Any language code?
That's why let's start with our examples.
It will become more clear, I guess.
Yeah.
Let's figure out what data structure we are using.
Yeah, that would be more beneficial. Let me open my screen. Okay. So this question, as mentioned, we have 2 courses, and this course is this is a prerequisite to do this course. Here is like 0, 1. This is an example of it.
Can you please increase the font size?
Okay. Is it okay right now?
Yeah, that's fine. Thank you.
Okay.
Much better.
Yeah. So here the question is saying some courses may have prerequisite. For example, to take course 0, you have to first take course 1, which is expressed in this pair. So if you want to do course 0, you need to complete course 1. Similarly, let's take an example of first, you want to complete course 1. Before that, you need to complete course 0. And we need to print the order of it. Similarly, here, 1 is dependent on 0 and 2 is also dependent on 0. So second example is, so 0 is the primary and it's going on 2 paths, 1, and let's say I put it something here, 2, and
if
so
you're
next,
using the Zoom, you can share a whiteboard to draw this. That could be easier.
okay.
You can use OneNote itself.
Yeah, I can put that only. Okay, so that is 0, 1, 2, and 3. So this kind of a graph is that which is mentioned over here. And so these are 4 courses, you need to print the order of it. So the answer is either 0, 1, 2, 3 or 0, 2, 1, 3. Is that clear?
And there will be cycles also.
Is that mentioned? The total number of courses of returning the order of courses you should take to finish. There can be a multiple order, you just need to return one of them. Yeah, so if it is impossible to finish all the courses, return an empty array. So that means they are expecting that there can be a cycle, and if there is any cycle, you need to print empty array. So anyone could start willing to do this with BFS or with the DFS, anything.
I mean,
I think I have the code in my code. I was reading the chat channel, and I still want to make sure that the runtime of this solution, how much what the guy think it could be, because I'm thinking that I'm still thinking of the DFS is big O of just n, because every node can be visited once, and even though whether we are using the BFS or the DFS, it seems that we still need to pre-process the input to convert the prerequisites into a map that mapping how many children for each individual node.
Yeah, yeah, we need, I think, so how we will be giving this kind of an array, and if we want to create a map, so this would be the key, and the values are the list of their children.
Yeah.
So, yeah, that kind of a graph map can be created in a DFS. Yeah. And if we are talking about the BFS, the same thing, we need that kind of a map. Along with it, we will be needed the in degree that, for example, let's take this over here. So we need to create an in degree map, like here 1 is dependent on how many in degrees are there, just 1, 0, and 2 is also just 1, and 3 is dependent on 2. So 3 in degree would be 2. So that is another map we need to create in a BFS. Is that the question you were asking?
Oh yeah, I think that partially yes. I want to make sure of this.
Yeah, you want to try that?
How the solution? I'm trying to find it out.
Okay.
I mean, I have a DFS. I did this like a month ago. I can.
Okay. You want to share it, or you want to?
I'll share it. I cannot complete it if I write it now.
Okay, I'll stop sharing.
I can put my solution in the chat.
Sure.
Let me know when you can see it.
Yeah, we can see the screen.
So I used a DFS approach here. So as Sonia just said, so when we are given a pair 1 0, so that means like a 0 is pointing to 1, right? So I mean I'm using C#, so the dictionary is nothing but just a hash map here. So which is I'm calling it as an adjacency list. So this part I'm first like putting all the keys into the map. So the number of courses, whatever we are given, is the length, which I'm using to populate all the courses as a keys in the adjacency map or adjacency list. So once I have that, I'm again populating through these prerequisites to build a graph. So this is the one which will give me the adjacency list graph.
Yes.
Okay. So then I'm actually, so I think this is this is clear, right?
Yeah.
So, and at line 17, so I'm just using a stack because since I'm using DFS, I need to, in the recursion, I need to store the values once I process all the elements. And if it is a last or a leaf or anything like which doesn't have any integrity, so then I'll add it to the stack. So then I'm maintaining one more data structure, visited, another one is a visiting. So since this is a DFS, so there can be like multiple graphs, independent graphs, right? So that's why I'm using for each loop to process through each and every key. In this case, it is every node, right? So for the DFS, I'm actually passing the adjacency list, stack, visited and visiting, and the current node from which I'm starting. Okay. So my DFS one is like, yeah, it's a base case. Like if it is a visited, I'll return it. And if it is not visited, I'm adding it to the visited and also to the visiting. Just in the visiting, we'll make sure like, I do not come across a loop. So again, this is like not a regular DFS. So I traverse, I get all the adjacency edges from that particular vertex. And if it is not part of the visiting, then I'll just recursively traverse. So this is a part, like once I'm at the leaf, or like, once I process all the things in the graph. So at the, sorry.
No, once you process all children, then you're putting in the stack.
Yeah, I'm putting it in the stack. Then I'm also removing it from the visiting. Okay. So if there are like independent graphs, like this loop will take care of processing all the graphs. So this is one I'm actually checking. So let's say if there are any loops, so the stack count may not be equal to the number of courses. So then I'm returning here the empty array, or the array with just one size of 1. So otherwise I'm constructing a result here. Since it's a stack, I am the expected is a array. So I'm popping out and populating the result here.
Can you show what you're returning in DFS method?
It's void.
It's void because I'm using a stack. So stack is maintaining the nodes.
Okay. Yeah.
One
You're pushing
optimization
everything to the stack.
you could have done, instead of returning void, you could have returned true false. So if you got a false at the top, you don't need to go further.
Yes, right. That's correct. Yeah. Yeah, that will avoid processing, extra processing, right? Yes.
And one check is over here only if your like visiting is already containing that vertex, then also you can return false because
Yes.
that is a
Right.
cycle.
Yes. Here I can, once I change it, I can return false at this point.
Yeah.
This looks good. It's clean.
Yeah, it's clean and everything is there. Any questions on this?
Still, what do you think is the running time of this algorithm? Because mine, if you look into chat, mine is very similar to this.
So here, we are visiting every node one time because if we haven't visited that, we are visiting.
Yeah.
So that's a check.
To me, it looks like a regular DFS with
Yeah.
just extra data structures used.
I think this line 53 is the one which is extra, right? We are just adding it after processing it.
No, that is it, which is keeping your result set. And if you comment 53, 54, this is then become a regular DFS. There's nothing special in this.
Yes, correct.
And the regular DFS complexity is like we are visiting all the nodes, which is on vertex plus edges.
I think so. That's just V plus E, the number of nodes and number of the edges.
Yeah, which is like V plus E. So how we are saying that its complexity is high? I'm not able to follow that.
Oh, this one is not high. I was talking about that BFS complexity is higher than DFS solution.
Shall we start with the BFS? Then we can see if what's data structure is making that complex. Anybody interested to do that with BFS?
I have a BFS.
Okay, can you share your screen if you want?
I was insisting the running time because recently I was asked in the interview about this and got challenged.
That's nice to be discussed there.
Yeah.
I think you can click the edit code.
If you can click the edit code, then we'll be.
It will give some more color. Thank you.
Can you see the screen?
Yes.
Yeah. Yeah, basically the same what you have said. I tried to create the in-degree and the adjacency matrix from the edges. So I'm incrementing that end and creating the adjacency matrix in this loop. And I'm trying to find the vertices with the in-degree 0. And I have a counter just to check how many vertices are visited, and to store the topological sorting in an array, and the same BFS loop. If Q is not empty, I'm trying to pull from the vertex and pull from the Q and increase the visited vertices. And I'm adding it to the topological sorting. And I'm getting the adjacency matrix for that. I'm getting the adjacent vertices for that particular vertex. I'm decreasing that in degree of the neighbor vertices. And if it is 0, I'm adding to the queue. And if it is, if both the visited count and the number of vertices are equal, I'm returning the topological sorting, else I'm returning a 0 array.
So in line 35, how many times do you think that is run in this line? That's basically the running time of the whole algorithm, I believe.
It will be V plus E only, right? I mean, for every edge you try to reduce the in degree.
And it's just going to, and it's order of 1 because it's going to that map and reducing its value by 1.
Yeah, but it's still executed, that's why. So the overall number of the executions should be big O, I think in this case, at least a big O of edges times the nodes, so V times E.
So the internal loop will execute. I mean, this whole queue will execute for V plus E times. So this will have the internal this for loop, the 34 to 40 will execute for every edge, and Q for every vertex. So it will be V plus E.
What does C?
Yes, so think it that way. It is a BFS. You only didn't put that in a queue. So if it is a regular BFS, you would have put in the queue. And later, if you have seen that as a visited, you would not have put in that in the queue. But what we are saying here, we'll only put that in the queue when the in degree will become 0. So basically, it is only going once in the queue. So let's say so if we remove this logic at line 36, let's say, then we have to introduce something like a visited set. Like if it is already visited, I will not put that in the queue. Correct? So then what would be the complexity? Then the complexity would be V plus E.
And we'll be putting that in only queue then because it's a 0.
Can anyone tell me what is C
like
here?
There is nothing like in degree here at line 36. And how we will decide whether I want to put that in the queue using a visited set. After I put in the queue, I will say it is visited. Next time if I see it again, I will not put that in the queue. Here the deciding factor is the in degree. So it's kind of same what I feel. So there also there is one deciding factor. Here is also there is one deciding factor. Only the deciding factor is different in a regular BFS and in this approach.
I'm confused. What your point do you think? What do you think that running time base? And what is C here?
One thing for me, can you comment line 36 and line 38? So now it became a regular BFS, right? Oh, and can you temporarily put something at line before line 37, like some visited set is there?
Okay.
Like let's assume there is some set visited and yeah, if it is not visited, then something like that.
Then in this case, the running time will be V plus E.
So if it is and after line 38, you will put that in the visited. That's it, or something like you will make visited true. So basically, you will after line 38.
You are asking me to write something?
Yeah, if you can write, so it will be more clear.
Yeah. What are you asking me?
You just make that as visited true. How you trying to something?
Okay.
Yeah, just make it true or something. Visited neighbor vertex equal to true, something like that. So now it is a pure DFS, correct?
I think so. Very
Correct?
typical.
Yeah, this is, and what is the complexity here? V plus C.
I wonder that what is C you're talking about? V plus C.
So
it's not C.
So first thing is I'm trying to come up with a hypothesis. Like, do you agree that BFS complexity is V plus C?
I agree.
Okay, so is this code is V plus C or not?
I believe so.
Yeah. Now, if now here the deciding factor was visited. Now, if you see at line 36 and line 41, we have just changed the deciding factor to in degree. Then why not it is V plus C?
Because I believe that in this case, the same node is visited multiple times rather than previously each node we visit only once.
No, there also you will check if it is already visited, you won't put that in the queue.
No, in the previous case, we won't mark the vertex to be visited. Once we visit it, we need to decrease the in degree that
No,
array.
let's not think about in degree. If it is regular BFS also, somebody
Okay.
I think starting in the mentioned, if it is regular BFS also,
Mm-hmm.
if you will again get that node back, you will say, okay, if it is visited, I won't put it in the queue.
If we use keeping this current code, like this is normal regular BFS, I agree that the running time would be the V plus E.
Correct. So if the node comes, so basically the node may come again, and that time will say if it is visited, I won't process it.
Okay, say that again.
So basically the node can come again, right?
Yeah, but the same node will be visited multiple times. Sorry, actually the line 38 will be will be went through. We got through multiple times. English. So then the code before we do this change, the running time should be multiple of the regular BFS solution, which is V plus E, and then it will be V plus let me see, V squared plus E maybe.
So the neighbor, the in degrees get how many times the in degrees getting reduced? Only the number of edges, right?
Only one is 0, so that means that 36 will be gone through
No. I
multiple
was
times.
talking about line 35.
Mm-hmm.
So the in degree will get reduced only till the number of edges for that, the number of incoming edges for that neighbor vertices, right?
I'm still confused. I'm still confused by this. So basically that's it. Let me try it in the channel. So basically we just run the visited something. Then this can be big O of 1. And now we are doing this, something like this, while the
Maybe can you just maybe if can you just print it and print the notes? Maybe that will clarify some things.
Sure.
So I'm putting in the chat. So here, please run the code only once, and this now it's multiple times. It's never going to be big O of 1.
No. That is what that in degrees reduced only till the number of edges, right? I mean, the 35 instruction is not O of 1, but it will get executed for the number of edges for that vertex itself. So in total, that 35 line instruction will happen for O of E times.
That E times, yeah. Let me think.
Are you getting doubt whether in a case of I mean whether there is a cyclic or something, or in which case are you getting the doubt?
Let me try another case. So let's say that this is the graph is a full graph that each node is connected to each other in one direction.
Okay.
So in the BFS running time, how many times each node will be visited? Maybe I can let me see. We can share my.
Should I stop this here?
No, what is general consensus? Because if we spend too much time, we're not able to proceed with other questions.
Because I feel like the running time will be a very good follow-up.
I feel it is V of V plus E.
Yeah, because if we are talking about the DFS also, if we are going, we are visiting every node, other node as well. Like we are following the path there as well, like all the edges. Here also we are visiting all the edges. Like if that edge is already in DFS, we check if that node is already visited, then we don't move forward. But here also, if that the other if we tweeted the course code before, here also we were checking that if it is visited, then we'll be not put that in our queue.
Yeah, I think as somebody was suggesting, like if after line 38 you put a counter plus plus and then print that value, you will see we can just find out like is it taking more than the number of nodes we have as a complexity, or I think it will be slightly more than the number of nodes for sure, because there is a for loop within a while loop. So that's what I think. But
See,
if you
if
want
there is regular BFS, still it would be same.
But this is not regular BFS.
So, but there is no change from the regular BFS.
We put a for, we put a.
See,
we
in
put
regular
it,
BFS also there are two loops, outer while loop and inner for loop. So how it is different from BFS, I'm not trying to find out.
okay, let's say we have a complete graph. I want to share. Can I share something?
I think you want to share. Yeah, I think.
Yeah, I want to share the
then
screen, at least my whiteboard.
I have to stop sharing. Yeah.
So I'm going to share a link, and they also mentioned that the complexity.
So let's say that we have this totally graph. So everything is connecting to each other. Yeah, the graph will be very messy. So in the regular BFS, so each node, they say that n equals, not v equals to 6. And so the edge should be how many? At least big O of the 1 v squared. So for the case that if so in this case each node will be if we do a regular BFS
or v 2 into v.
Huh?
It should be v squared or 2 into v. You are saying
v squared, and because I can't draw too many lines in the graph, but let's assume that each line, each node is connected to each other in one direction.
Yep.
And so the BFS each node, for example, this node A, B, C, D. Let's say that the node D will be maybe F. So node F will be visited only once in the BFS solution.
No.
Why?
When you are at C, you will again try to go towards F.
F, and at B as well, you will be trying to go to F.
Yeah. Until you break the link between B and F.
Okay,
so what will go in the queue first? You will first put A in the queue, right?
Yeah.
And can you also create a visited set beneath that?
Yeah, or we can put the color of this it. Oh, okay. Yeah.
Yeah, either way. So you
Yeah.
will put A in the BFS.
Yeah, when we visited A,
and you will put
A in the visited node.
And then you go to and you then put all neighbors of A, which is D, E, and F.
Yeah.
And B as well.
No, sorry, B, D, E, F.
Yes.
Yeah, B, D. Yeah, all of them. And
Can you put that in the queue?
in the queue, let's say that
B, D,
E, F in the
and
queue.
then you will make all of them visited. B, D, E, F
Yeah.
are visited now.
Yeah.
Then you will remove B from the queue.
Yeah. Then
And you will try to put F also.
yeah, because
So
F is already visited, so we don't take any further action.
Yes. So same thing. You again have went towards F. It's not like you haven't went towards F. And in the same solution which Uday was sharing, we only take action when. So here the action is you have already visited. You won't visit it again.
Okay.
So there the action is when the degree will become 0.
Because F is visited and.
So think in that way.
I see what you're talking about. Okay, that makes sense. So in this case, yeah, I have no idea what's the running time now because it seems that F is visited multiple times in this way. So yeah, let me think about this over. Because I still feel like something is visited multiple times, but yeah, maybe you can keep going and I can text them back in this Discord channel. Sound good?
So
yeah, we
is
can.
there any more to, yeah.
We can discuss in Discord later.
Okay. Yeah.
But yes, this is a good discussion. Thank you, Aaron. You spell your name as Aaron?
Yeah, that's my name.
Okay.
And I'm the visitor today, new to this thing.
Oh, wow.
Oh, wow.
Welcome to the meeting then.
Okay, can we move for the second question then? Is there any doubt in the first question, BFS or DFS approach? So, because next question is also very lengthy, I suppose.
I think let's move on. Yeah, that's good.
Okay. Can you see my screen for the second question?
Yes.
So this question is, we have given, there is a new alien language which uses the Latin alphabet. Here the order among letters are unknown to you. This is a list of non-empty words from the dictionary, and words are sorted according to lexicographically by the rules of this new language. So we need to derive what's the order of the letters. Sorry, one second. Where is my screen? Okay. Sorry. So here the lexicographical means like we need to check what's the lexicographical means over here. So we have WRT and WRF. So there, which shows that WRT is here. WRT is smaller than WRF. But here, so here is we have two strings which are same like until WR. So here, what's the difference is like T is smaller than F. So one rule is like which tells us that T in order of the dictionary we have T will come before than F. Like how we in our journal English alphabet we have A, B, C, D, F, and if we want to check is A is smaller than B, what should be the answer in a lexicographical way? It should be true, because yes, A is smaller than B. And if I want to check is AB is smaller than B, what should be the answer?
That should be true.
Yeah, because here, why we are checking that? Because A is smaller than B. Here, the other one, this is one rule. Like, if there are, one rule is like, if there is two strings which are matching, will match until or unless there is a string which is not equal. And the other is like, if we have the different lengths, then also if we are matching by first character, if we match the first character that A is smaller than B, will not need to move forward to match the other characters. So here, if we can see in this example, if we compare these two strings, T is smaller than F. So let's say we have T and then F. Then if we compare these two characters, these two strings, W, which means that W is smaller than E, then we'll be like, let's say W, another is W is smaller than E. And R is also smaller than T. So for here, we know that R is smaller than T. And R over here, R is smaller than F. And W is smaller than E. So if, and here, by comparing these two, which we can make sure that E is smaller than R. So here E is smaller and then W. So this is one result. And how we'll be able to solve that using topological sort? That's another thing, but we need to make sure that what's the lexicographical order is telling us. So here Z, we have two strings Z and X. And so this is a simple correct. Z comes before X. So Z's just output should be like ZX. And here, another input is ZXZ. So if you can see here, first string is Z, other is X, and next is Z. So by comparing these two strings, we are making sure that yes, Z comes before X. When we compare these two strings, there is which is invalid, because that is already saying that Z comes before X. But if we are comparing this, which means that X is coming before Z, which is not valid. So if it is not valid, we need to return empty string.
Basically, it will form like a cycle.
Yeah, it will form like that. Is that question, any doubt in this?
So the order of the strings we are deciding from the input basically. So I mean Z is coming before X is based on the input. But in alphabetical letters, that's not the case, right? So what we are saying is that based on the input, we are saying that Z is before X.
Yeah, based on the input given, we'll need to form our alphabetical order. We'll not think about here in this question like the actual alphabetical like A, B, C, D.
Got it. Got it.
Yeah.
Yeah.
Yeah, this is a kind of you'll be creating a new language, and based on the strings which we have given. Any other doubt?
So in example 1, do we compare WRT with each and every string and come up with the pattern? Like first string with the second, first with the third. So do we compare?
Yeah. So yeah, we need to compare we'll compare in our, like if we are traversing this array, we'll be comparing these two, then these two, then these, like this. Because why we are comparing these like one by one, why we are not comparing this with this first and third? Because if this is lesser than this, that means that this is automatically will less than this.
Oh, that makes sense.
Yeah. Think like it's an increasing order. we are already given in, so it's written that it's a sorted lexicographical. We have already given a sorted array, and we need to form a new kind of words.
Yeah, it's unnecessary to compare because it's already sorted.
Yes, yes.
Incrementing. Got it.
And I think the best way to solve this problem is using topological sort with BFS. Because we'll be able to visit its character like one by one. I found it's easy to do, but
I think DFS could also be used, but
Yeah.
DFS would be easier to visualize.
Anyone interested to solve this?
I have a solution. Can I share it?
Yeah, sure. Let me stop sharing. And this question is a logged question. So if anyone wants to do that, so it's we can share the code and they can solve it.
Let me know when you see it.
Yeah, we can see that.
Okay. So I mean, earlier I saw this like a couple of months ago. I mean, I initially tried with BFS, but later I went with BFS. So there are like 3 steps. So the first one is converting our input to adjacency list or a graph. Right?
Yeah.
That is I think main meat of the problem. So once you have that, the other BFS approach is similar to what we discussed in the earlier problem.
Are you creating the in-degree count of it as well?
Yes.
Okay.
So since these are the characters, so I'm taking a integer array of size 26. Then I'm taking a map. This is a line. This is dictionary, which is a map to create the adjacency list. So then I have this method where I'm actually creating the adjacency list and also calculating the in degree of for each word. Okay. So first, I'm actually I just always use this approach. So I'm populating the list of keys in my graph.
Mm-hmm.
So when I say keys, like there are like different nodes, right? Whatever the available nodes we have, I'm populating in this graph. Okay. And at line 26, what I'm doing is I'm actually trying to get the adjacency list. Like first, if you look at this, we are comparing these 2 words. So I take the minimum or minimum length of these 2 words. So whenever I find a difference between the characters, like when there are like when the 2 characters in the previous word and the current word, I mean, there is no difference. So I cannot, there is no edge from one node to another, right? So I do not calculate anything. I continue my loop until I find a difference. So I'm starting it from the first index so that I could compare it with the index 0. So I'm taking the minimum length. So I have, I'm taking the previous character and the current character. So if I find a difference, so I'm just for the particular node, I'm just checking whether that already contains, because there can be duplicate, right? So if it does not contain, I'm just adding the edge. So if you look at the first example, from T to F, there is an edge. So the previous is T, and T, I'm adding adjacency node of F, character F. And here I'm updating the in degree of F, because there is a edge from, in this 2 words, there's a edge from T to F. So the in degree of F is 1. So I'm just incrementing the in degree here. So once I find a difference, I do not need to calculate the other, I don't need to compare the other characters, right? So I'm breaking.
Because that won't account into this lexicographical sorting. So if you already if you already got to deciding factor, then the rest are not needed.
Yes, yeah. I mean, actually, this is a point where I actually struggled a lot.
Yeah.
Didn't know that I had to stop, so I was continuing, and I couldn't. I mean, I had to struggle here. Like I spent a lot of time to calculate this part.
Because
So,
like Sonia mentioned, if you have A, B, and A, still this A would be smaller, so you don't need to go further.
yes, that's correct. Yeah, right. I think that's the main key point while calculating this adjacency list, right? So once I have once I have the map, I'm calling the BFS, which is at line 8. So to this BFS, I'm passing the string builder because I need the output in the string. So I'm passing the graph and also the in degree. Okay, so this is my BFS. So in the BFS, I'm using a queue at line 50. So initially, I'm populating the queue with the number with the edges, because first I'm getting like list of nodes I have in the graph. So I'm checking what if I'm checking in the in degree what are the nodes which have in degree is equal to 0.
Mm-hmm.
So I find those nodes with the in degree 0 and I'm populating the queue.
Mm-hmm.
So if my queue is not empty, then I dequeue the character. Okay, and once I dequeue it, that is my results. So I'm adding it to my string builder here at line 59. And I check whether if there are any edges from that particular node. If there are any edges, so so this is a loop we discussed in previous question. So I get the adjacent nodes and I reduce their in degree. So while reducing the in degree, I also check once after reducing, if the in degree is 0, I'm adding it to the queue. Okay. So I mean, the loop goes on. I mean, if there is any point of time, if the in degree is if I don't find any characters with in degree 0, then the loop will come out of this because the queue will be empty, and I'll return the string. So if we cannot process all the strings, then the length will not be equal to the number of the nodes. Then I'll return the empty string. So one such example is the third example. So you have from Z, you're going to X. So the in degree of X will be 1. Okay.
Mm-hmm.
Again, from X to Z, there is a edge. So
in degree of Z would also be 1, yeah.
Yeah. So while traversing in the BFS, so this particular loop will not find any character or a node with in degree 0.
Mm-hmm.
So then my while loop will at 56 will not execute, and I'll get an empty value, empty string from this BFS. If I have an empty, but I have number of nodes in my graph is 2, so then I'll return empty string.
And there is, I think, one more catch here. They recently updated the test cases. I think if you submit it, will not work.
Okay.
If you just submit it.
Yeah. Okay. I did this, I think 2 months ago. Yeah, I think 3 months ago. Yeah.
So yeah, this case is even I got failed because they have added recently this particular case. Why it is? Because here we can see that the first string is greater than the second string.
Yes.
Because why it's greater?
Basically, this is not a valid lexicographical order.
Yeah, this is not a valid, and I don't know why, because they already mentioned that they'll be giving the sorting one, and this is not a sorted. In the question, they mentioned that this is a sorted lexicographically order, but this is not a sorted one. So that's a catch with them.
So
that
ABC
why,
is greater than AB.
Yeah, this is ABC is greater than AB.
So if you want to fix this, you can just do a line where you are building your dictionary.
I'm getting a minimum here, so maybe.
Yeah, there is another case you can add over here where you are printing your this.
Can you go down a bit?
Yeah.
Where you are doing a break.
Yes. After
So
this,
at line 43.
One other case you can mention at 43.
So here.
Yeah.
Okay.
Like you can check that if the previous, like if your length is same, you have reached your, if your pointer j is equal to your length, minimum length you have reached, and but your
I need to return, change the return type of my. Okay, yeah, I think.
So here it's if the pointer is equal to j, no, it is equal to j. If the minimum length is equal to j, you have reached that level that yes, like like if you are like AB is equal to AB, but the previous uh, the previous one is greater, the length of the previous one is greater than the current one, then you can't move forward or you can return what you are returning over here, I think.
So then that should be the case at this place, right? When I'm
You can just
calculating minimum.
you can just make your graph as equal to new graph. That's it.
Yeah, graph should be equal to new graph, and in degree should also be, you're changing over here, no, so yeah, graph should be equal to new graph.
And then you just put a return there.
I have to, okay, I have to new up those both the objects. Okay.
So in degree would also be the new one, because there is nothing you should put over there, because that's not the valid case. It's like you are verifying your there's a question of verifying the Arabian dictionary, and here they have you are verifying that your dictionary is not valid.
Yes, yeah, correct.
Yeah.
Yeah, I think I this condition may not. I have to put like I have to think.
You can put over here just like previous, if minimum length is equal to j, and your previous length of the previous string is greater than the current string. Just compare that along with this.
Like
he's not adding any edge, right? I mean, he's adding edge only when there is a mismatch. But since the length is minimum, the edge won't get added. So all the vertices A, B, C will be having. I mean, I'm not sure how many vertices are there.
You are doing correct, Sandeep. So
Yeah,
basically,
I
it
mean,
is checking whether it is actually a valid dictionary, a valid order has been given or not. So if you
there are
write
no edges.
previous length greater than previous dot length.
Previous, you have already baked that word. Previous dot length.
Oh, sorry. I think your words I minus 1 greater than dot length.
Dot length.
Greater than words I dot length. Then you can just reset your graph.
Okay.
Is equal to new something.
I think in the case we can simply
Can't we check whether there are new edges or not?
No, then we don't need to check further because the dictionary itself is the input itself is bad. So you can say graph equal to new graph. Graph equal to new dictionary, and then just return. Also write return.
I think you need to do the in degree as well. You are defining.
No, I don't think so. In degree is needed.
Okay.
You have to also write return.
Yeah.
At line 46.
Oh, I need to return because I'm not returning.
No, you can just write return.
Just return. Okay. Oh, got it. Okay, because okay.
It will come out of loop and then it won't do anything further.
The BFS will return empty. Okay.
Your graph will be empty and nothing will happen then after that.
Okay.
Now I think you submit, it will work.
I think that case you need to. Yeah, that case still was not checked.
Instead of the check, we can add whether there are edges or not, right? If there are no edges, we can't find the topological sorting, right?
Because here he's actually breaking, no? So if he moves this 43 above 34, then it might work.
Either way,
you because here it is comparing that minimum length as well.
Oh, there's a break state.
Yeah, but this will not execute, right? Because you did not find any comparison. I'm taking.
Oh, yeah. There is no comparison. Yeah. I think this should work. I don't know why it didn't work. Let me.
No,
Is it because of
I'm taking a minimum length, so it doesn't enter.
So can I speak?
It
Yeah,
should.
there are no edges actually. So there will not be any, I mean, all the vertices will, in degree will be 0 itself.
I think it's
That is why ABC is coming.
Sandeep was mentioning.
If you check whether the edge, if there are any edges or not, then we can, if there are no edges, we can't find the topological sorting. And we can add a check whether there are any edges or not.
Yeah, maybe I just have to initialize in degree array to maybe.
Yeah, in degree as well. In degree is equal to, yeah, you can check is equal to new.
No, not new, because I'm basically I'm by default when you new up it, all the values are 0. Maybe I have to initially, when I'm using this, I have to populate in degree with -1.
Yeah. Yes.
Cover, right?
You can do like something like arrays dot.
I'll just.
I think I also did the same thing. I made it -1. Because everything it will consider as 0.
Yeah. So
now it will work. Yeah.
Now it will become worse, right?
No, you need that.
It will become 0, right? If there is an edge, the in degree will become 0.
Can you put the test case?
Yeah.
Yeah. Well, great.
I think if you comment 47 to 48, it won't work.
Is it? Okay, I just
like you were saying, telling to remove it. Okay, it worked here also.
Can you test the positive test case?
Yeah, because actually earlier he was using the whole 26, right? So that is not a extra space he's using there.
This is failed. So can you put the code which you commented earlier and try to run this again?
No, that code was not impacting.
No. I mean, the -1 is becoming 0. So
yeah,
instead of, I mean, either special handling needs to be there. If -1 increase it to 0 and then increase or something like that, or whether there are any edges, something like that.
Yeah, basically here actually I need
just increasing the value there, right? Yeah.
Put a condition here. If it is -1, then I need to.
Or you can put the condition if it is able to add, then only you do it. Like if you are able to add that in a here.
Yeah, I think maybe that is solvable, right? Yeah.
Yeah.
It's not a big deal. Maybe we can take this later and then put it on our Slack.
Yeah, I'll do that.
I can paste my solution, like if you want.
Please, yeah.
Like, do you want me to show my solution?
Yeah, quickly run through that. Should be good.
Okay, 1 second. Share the screen. Here, the same thing, like creating and did -1, creating it. So the main thing is this, like, which I am saying, I have taken over here a set to add those in my dictionary, And if it is able to add, then only I am incrementing it. And this check is over here, and I'm clearing my map. Here I have given my return type as map. So, yeah. So to avoid the duplicates, I use set if we have taken the link. So that's why I've taken the set over here. Is there any question regarding this? Because it's the way is like same. I am instead of just list, I have taken a set to add those in adjacent. They are actually neighbors to that list, and while creating a map, this like I have created a new set, and the main logic is if I am if that word I able to add that word in my list, and then only I'm making that count. And rest is like I'm just comparing it. Is there any doubt in this? Or do you want me to run this with that example?
Yeah, just go ahead and run that. Yeah, it's fine.
If I run with this, that case passed, and I just changed that to.
I think the only thing is they are contradicting their input.
Yes, their question and their example test case is not matching.
They told where words are already sorted, but this is wrong input.
Mm-hmm.
But it's good, like it would check if it is wrong input, then it won't do anything.
Yeah, this is just a special case, right? We need to handle
Yes.
it.
Yeah, this is actually a really, really special case.
Yeah.
But this is exactly same as the other question, validating alien dictionary.
So yeah, if this kind of a problem is an interview, you need to ask it before, like, is there will be a sorted, or is there any chance that there is no validation? I need to check that. So if we want to validate that as well, then yeah, we need to add that.
So if the interviewer say that the input could come any order, then we have to, I think, account for that. But
yeah.
Already this question is so lengthy, I don't know.
Yeah. So many special cases to consider. Yeah, that will be a big thing in 45 minutes.
Yeah. Okay, so there is a last question that's a bonus question with parallel courses. We have just 2-3 minutes, so I'll just walk through over here. So that's a same question. We did the first question, like there is 2 courses here. There we check this y is dependent upon x, but here x, we need to do x before y. So that's just the way they have put it. And here is like you need to do 1 and 2 before 3. So what they are asking is you need to tell what are the minimum number of semesters needed to study all the courses. So think like, and you can study as many courses in one semester. So think like this can these 2 courses can be done at one semester, and this course can be done at one semester. So that's why the answer is 2. And think for the second example, this is a cyclic form, as we mentioned previously as well. If it is a cycle, we'll not be able to form any sorting form, then this is not a valid example. So this is like we'll be returning -1 over here. So Here also, like BFS, the regular BFS taking an in degree, and then shall I share the its solution and which will be more clear, or just I'll walk through it? What's your?
So here you are like, while doing the BFS, you're calculating the number of levels. Is it correct?
Yeah, so that's also a good thing. Like there is an inclusion of a level order as well. So for example, when in the BFS, what we were saying that if all the nodes become 0, then we'll be add that in a queue. So what's the level of, what's the in degree of these would be 0, correct?
Yeah.
And so this would come at a 1 level. This would be the level 1. And while putting those in, removing that from a queue, then we'll also, in degree of this would also become 0, correct? Because after visiting these 2 nodes,
yeah,
the second part is that we'll be putting 3 as well. So let's say initially our in queue we have 1 and 2, and 1 degree in degree was 0, 2 is also 0, and 3 was 2. So first of all, we need to remove the zeros one. We need to add those in the queues which have 0, and so this would be in a level 1. While solving this problem in a queue, like while traversing, we'll be increasing. We'll take a 1 counter. Say that if 1 level is completed, we increment that counter. So now next, after we'll be visiting all these 2. So this, if we remove 1, then its count will be 1, and if we'll remove 2, the count will be 0. So in next part, we'll add 3 in our queue because its in degree is 0, and so its in degree is 0. While we're traversing, our level would increase to 2.
Yeah.
Because the counter will increase because we are complete. We reached on 2nd level.
Yeah, got it. Thank you.
Yeah. So that's one problem. So this is the same like BFS, the same same solution. The only logic is we need to return. Earlier we were returning in a 1, 2, 3 in an ordering way. Here we need to return the minimum the levels we have taken to solve that. Okay, I'll post this solution in a chat.
We think like a cloud formation stack in AWS. So things which can be like you are doing RDS, SQS, and Lambda is dependent on SQS. But RDS and SQS can be installed in parallel and then followed by the Lambda. So if you have seen CloudFormation stack, it happens there. Things can be deployed parallel, and which are dependent, they will come in the next level.
Yeah. Okay.
Okay.
So any doubt?
So this is just the last question was basically topological sort implementing the level order traversal, right?
If you can share you can show your solution. That.
1 second, let me open that. So many tabs open. So here also, I have created a map which is like in degree. Initially, I have initialized with 0 all the nodes, and made the course map graph, like what are the adjacency lists. And here I have taken the list, and I have also encountered if that course is dependent on other courses, I have incremented that counter. So the main logic is over here, like here I'm just adding initially in a queue if they have a value is equal to 0, like if they are not dependent on anything, like 1 and 2 I've added in a queue. I've made the counter semester. I want to know how many which we need to return, minimum number of semesters. Here is the typical BFS, like I have taken the size of the queue and I am solving this size, and if I completed that that row, for example, this level, I've completed this level, then I am incrementing my semester. So this is the same thing which we were doing earlier, like popping up your element and traversing your adjacency courses, then here, and you're decrementing your that course counter in degree count, and if it is reached 0, then you are appending in your queue.
Yeah, that makes sense.
Yeah, and because we have mentioned, like initially we have 1 and 2, and if your length of your queue is like size is done, then you will be out of that while loop, and you will be incrementing your counter. Here the extra logic is like at the end case, here is like if you're not able to reach that point where it's n is equal to 3, and you're not able to pop all the elements, then there will be a mismatch and you need to return -1.
Okay, yeah.
Yeah.
Makes sense.
Is it clear?
Yep.
Okay, perfect. I'll share the code in a channel of ours, and please let me know.
Sure.
Okay, then thank you so much.
Yeah, thank you. It was a good session. Yeah.
Thank you so much.
We learned all the variations of the topological sort implementation. Yeah.
And yeah, that's the best example, because I have seen this lot of questions. Sometimes it occurs in a coding challenge we have, or sometimes in an interview. So these kind of questions are very important to do. I think so.
Yeah, no, that's good.
Okay, I think we can stop the recording. And, yeah.
Thank you for the